Now let us discuss Gauss's law. Gauss's law is used to calculate electric field. Although electric field can be calculated by various other methods, as we've already discussed, that if there is a point charge, electric field can be directly calculated by E is equal to KEQ upon R square. Okay. While if there is an extended object, extended charge distribution, then you know that electric field can be calculated by integral of KE dq upon R square. Okay. But if there is a symmetric object, symmetric charge distribution, then we use Gauss's law. So it means that electric field for a point charge can be calculated by a simple formula, which is KEQ upon R square. For an extended object is the integral of KE dq upon R square. While for a symmetric charge distribution, we can use Gauss's law, and it is the easiest way of calculating electric field. Now, it is so. I would like to summarize Gauss's law. It is valid only for symmetric charge distribution. If the charge distribution is not symmetric, then we cannot use it. And so, how to use Gauss's law? First of all, what you have to do is you have to draw a suitable closed surface around the charge distribution. Now in your syllabus usually you'll have charge distribution which will be a sphere, usually maybe a positively charged sphere, an insulator or a conductor depending on the situation, or you might have a cylinder, or you might have a line charge. So in this case, suitable means that it has to be such that the electric field is usually either parallel or perpendicular to the area vector. So if this is the charge distribution and you want to find out what is the electric field at, let's say, at this point, then just draw a sphere around this point and then on this sphere, on this area, see what is the direction of electric field and area vector. Okay. So this is the first thing you have to do to use the Gauss's law. Second is check the angle between electric field and area vector at each face. Now if it is a sphere, so you know that because it is positively charged has electric field radially outwards in all the directions. So, and the area vector on a sphere is always perpendicular. So let me just draw it somewhere here maybe. Okay. So electric field and area vector will be in the same direction at this point. Now this is a particular example I've taken for a sphere, but you can also take it for a cube and check what is the direction of electric field and area at each face. Or you can also take this example for a wire, draw a cylinder around it and then check it. Okay. Now, so we check the electric field and area vector and the direction angle between them. So in this case we know that at each point they will be parallel to each other. So at each point, so we know for this particular situation they are parallel to each other at each point. So if they are parallel, it means theta is equal to 0, and it also means that E vector dot dA vector will be equal to E dA cosine of 0. Now cosine of 0 is 1, so it will be equal to E dA. So, and then you have to check the charge enclosed by this surface. Now if the charge inside this surface is capital Q or small q or whatever it is, just check what is the charge enclosed. So that charge enclosed will be, like in this case it will be capital Q, while in some other case it might be something else. So whatever charge is inside this surface, just check what is the charge and then just use the Gauss Law equation, which will be E vector dot. Now you know the angle, you know what is the area of a sphere, you know what is the charge enclosed, and you also know this is a constant. So it means that this is the area of imaginary surface. So let me write it here. So if you have to conclude Gauss's law, then this will be the area of imaginary surface which we draw around the charge distribution. It might be a cylinder, it might be a sphere, okay? And the electric field, now electric field and area vector together. So this will be the electric field on the surface. Imaginary surface which we are talking about here. Okay, and this will be the total charge inside the imaginary surface. Okay. So we'll understand it better by taking some example in the next video.